Alright, hello everyone. So I'm left with two more topics in consumer theory, liability preference and aggregate demand. So I'm going to take a pair of lecture videos about these two remaining topics. So let me start with the liability preference. That is another important topic in consumer theory. So unfortunately, I can't skip this topic. So let me spend some time in this lecture video to illustrate the basic idea of this liability preference. Okay, so in order to introduce the liability preference, we needed to go back to our previous analysis. So far what we have done, we try to make a prediction about the consumer's behavior in the market. Okay? But this analysis is based on the demand function, the Wallachian demand and Hicksian demand. So we derived from these two demand functions from the two optimization problems. Utility maximization problem and the expenditure minimization. But when we formulate these two problems, we had to make sure the existence of a utility function, because if we think about the statement of UMP, we assume that in the UMP we assume that consumer chooses one bundle so as to maximize utility given budget constraint. So in the formulation of the UMP, we have a utility function. It means without the utility function, we can formulate the UMP. Okay, so we can derive the Wallachian demand. But it turns out that utility function does not always exist. It does exist under some certain conditions on preference relations. This is why we initiated our analysis with this preference relation. Okay, so we began by making several assumptions on preference relations, from rationality to convexity. And under those assumptions, we can make sure that there exists a nice utility function, and from that we can formulate the UMP or EMP. Okay? And from the first optimization problem, we obtain our first prediction about the consumer's behavior in the market. Okay? And for the second Hicksian demand, we consider the dual problem of the UMP, and where there is a certain level of utility consumer wants to attain, which is called the target utility. Okay, so we need information about the utility function even in that EMP. Okay, and then we figured out what is the cost minimizing bundle, for achievement of that target utility. That gives rise to Hicksian demand. Second prediction about the consumer's behavior. Okay, so additionally, we also talked about the general properties of these two demand functions. So for Wallachian demand, if we go back to the previous proposition, remember that if X star is a Wallachian demand, so if that is the solution to the UMP, and we know that first Wallachian demand is homogeneous of degree 0 in price factor and wealth. That means if we increase P and W by alpha P and alpha W, so if we increase price factor and wealth alpha fold, yeah, this optimal choice, so our prediction does not change at all. This is due to the property of the structure of the UMP, because in that problem we assumed consumer chooses one bundle to maximize this quantity, this utility function, subject to P dot X is smaller than or equal to W. So given this budget constraint, so a change in parameter P and W does not affect the objective function. This function is independent of these two parameters. But a change in P and W may affect the budget constraint, but under this configuration, so if we increase P and W alpha fold, it does not change the budget constraint either. So the consumer will encounter the same optimization problem, so the optimal choice should be the same. So the first property of this Wallachian demand is due to the structure of the UMP. And the second property was the Wallace law. The P dot X star should be equal to W. In words, for utility maximization, consumer has to exhaust all of his disposable income. Yeah, so optimal choice must be on the budget line. And that is a very simple result from the assumption we made on the preference relation. So under either monotonistic condition or a little bit weaker condition than this, local non-satiation assumption, we could make sure that Wallace law is indeed satisfied. Yeah, and there is one more property about the convexity and uniqueness of this Wallacian demand that also depends on the extra condition on the preference relations. So more specifically, if the preference relation is convex, then the set of Wallacian demand is going to be a convex set. And if we strengthen that assumption to strict convexity, then we know this Wallacian demand is uniquely determined. Okay? So that also depends on the assumptions on preference relations. And when it comes to Hicksian demand, we established one property, that is the Slotsky equation is symmetric and negative semi-definite. So the Slotsky equation was defined as the derivative matrix of this Hicksian demand with respect to price. Okay, once again, Slotsky matrix is the derivative matrix of this Hicksian demand with respect to price. Okay, so in case of two commodities, it's going to be 2 by 2 matrix. So in the first row, we put the demand for good one, Hicksian demand for good one, and then take the derivative with respect to P1 and P2. In the second row, we put the Hicksian demand for the other good, and do the same job. Okay, so take the derivative with respect to the prices. Okay, so it's going to be 2 by 2. In case of L commodities, we are going to obtain L by L dimensional matrices. So L by L dimensional matrix as the Slotsky matrix. Okay? So regardless of that dimension, what we can say in list, we can say this matrix is going to be symmetric and negative semi-definite. Okay, and the last property is due to the structure of the EMP, because and the properties of EMP. So the value function of the EMP expansion function has nice properties. So by Shepard lemma, we know that Hicksian derivative of this expansion function with respect to price is going to be Hicksian demand. Okay. So each entry in this Slotsky matrix is going to be, so it can be seen as, so it can be regarded as the second order derivative of this expansion function with respect to price. For example, this guy, this entry can be written as second order derivative of expansion function with respect to P1 and P2. Okay, and furthermore, what we know from this expansion function is the function is concave with respect to price. Okay? So by definition of the expansion function, it tells us minimal expenditure. So minimal expenditure is increasing as price increases, but at a decreasing rate. Okay, so it shows some concave pattern with respect to the change in prices. Okay, and so the Slotsky matrix can be thought of as the Hessian matrix of expansion function by the Shepard lemma. Okay? And we know expansion function is concave. Okay? So the Hessian matrix of that should be negative semi-definite. In other words, Slotsky matrix should be negative semi-definite. Okay? So from the in light of the structure of the EMP, we established one more property about the So one more property about the demand function. Okay, so that is the positive theory about the consumer behavior we developed so far. Okay, and this analysis is often referred to as the preference-based approach. Preference-based approach. In the sense that, because we initiated our analysis by making assumptions on preferences. Yeah. So without preferences, we can't think of a UMP or EMP, because we can't think of the existence of utility function. So we can't think of the Wallachian demand or Hicksian demand. So every component and every property, of our prediction is dependent on the preference relations. Yeah? So this is why we call the previous analysis preference-based approach. But there is one major shortcoming with this approach, which is, so we began by making assumptions on preference relations. But preference relation is innate, but it is not observable to analysts. Yeah? So we have although we have a nice understanding about the preference ranking, we can observe that from the data. Yeah? So theoretically we can define that, but we can observe from the data. So we began by making assumptions on what we can't observe. Okay? So that is a major shortcoming with this preference-based approach. Okay? So alternative approach suggested by Paul Samuelson, who is known as the founder of modern economics, is that instead of making assumptions on what we can observe, what if we impose restrictions or conditions on what we can observe? Okay? Hicksian demand is not observable either, because it depends on the target utility. Target utility also perfectly makes sense, but we can observe that from the data. Okay? But in contrast with the Hicksian demand, Wallachian demand is observable, because it depends on the two observable parameters. Yeah? We can observe the current market price, and we can observe the consumer's income. Yeah? And we can observe the actual choice made by the consumer. Okay? So we can think of the relation between consumer's actual choice, okay, and these two observable parameters, P and W. Yeah. So without the aid of UMP, we can still think of the relationship between these two, and we can observe the relationship between these two from the data. Okay? So, in order to distinguish that relationship from the Wallachian demand, this Wallachian demand is a theoretical prediction. That is the final result, in this preference-based approach we can obtain, right? So that is the final result from the UMP. That is actually our prediction. But now we are going to start from the relationship between these two we can observe from the data. Yeah? So let me call this, without the asterisk superscript, choice function. Okay? So to separate from the Wallachian demand, once again, this is a theoretical prediction, which is derived. Okay? That is not we observed from the data. That is what we derived from the UMP. Okay? But now we are going to talk about this choice function, the actual relationship that we can observe from the data between the consumer's actual choice and these two parameters. Okay? So the definition of this choice function is right here. X of P and W without the asterisk superscript denote the choice made by the consumer given price vector P and wealth W. Okay, so the basic idea of reward preference can be thought of as, can be understood as the reverse engineering of this preference-based approach. Under the preference-based approach, we started from the preference relations, okay, and then we formulated these two optimization problems, and from that we can obtain some predictions. Okay? But now we start from this choice function. Okay? And then we are going to make assumption on this one. Okay? And then in the end, we are trying to deduce preference ranking. Okay? So the basic idea of this related preference is from the observed data, we can deduce consumers' preference ranking. Okay? And that we are going to make just one assumption on this choice function. That is known as the weak axiom of labeled preference. Okay? That is a very simple and sensible assumption, and that is necessary for minimal consistency. Okay, so I think you guys have seen this weak axiom when taking the intermediate level of microeconomics, but the formal definition also shows up in Musgrave Winston Green in chapter 2.f. Okay, now let me remind you of this definition. So once again, we are going to make assumption on the choice function. Okay? That is different from the Wallachian demand. So we say the choice function x satisfies the weak axiom of labeled preference. In short, WARP. So WARP. If the following statement holds, okay, and in this statement we have two different levels of price vectors and two different levels of wealth. Yeah, so we have P and P prime and W prime. Okay? In other words, we have two different budget sets. Okay? One budget set with this P and W, and another budget set with this P prime and W prime. Okay? And to simplify the notation, let me call the actual choice made by the consumer under this scenario. So under this budget set, P prime and W prime. So the choice function's value at these two parameters. Okay, and let me call this bundle X prime. Okay, that means we observed consumer chooses this bundle X prime under this budget set. Okay, and the actual choice made by the consumer under this configuration, P and W, bundle X. Okay, let me call that bundle X. Okay. So bundle X indicates the value of this function under these two parameters. Okay, then the first inequality can be written as P dot X prime is smaller than or equal to W. Okay, and bundle X prime is different from bundle X. Okay, then work requires P prime dot X is strictly larger than W prime. Okay, and then the way to understand this statement is, piece of cake, because this inequality tells us, under the current budget set P and W, X prime is affordable. This choice is affordable because the total expenditure for this one does not exceed the current wealth. And by definition of this bundle X, that was the chosen bundle under this current budget set. This bundle was also affordable, right? So between these two affordable alternatives, we observe that consumer choose this bundle X instead of this X prime. It means it reveals that consumer prefers bundle X over bundle X prime. Okay, so this statement tells us X is revealed preferred to X prime. Okay, then why did we observe consumer choose the bundle X prime? Okay, X prime under this configuration, so under this budget set P prime and W prime, because the previous bundle X is not affordable in this situation. Okay, so p prime dot x should exceed the width w prime. Okay, so the basic idea of this weak axiom is highlighted in the last bullet point. Okay, so if the consumer chooses one bundle instead of another, then the former should be considered to be labeled preferred to x prime. Yeah, so the weak axiom can be thought of as the completeness assumption we made on the preference relation. Okay, so once again, in the labeled preference approach, we are trying to deduce the preference ranking from the observed data. Okay, but if we assume the warp on this choice function, then the deduced preference ranking is going to be complete. Okay, in the following sense, I think the basic idea of this warp will be clear after looking at these two examples. So in this example, so we have just the two commodities. So let me put the demand for good 1 on the horizontal axis and demand for good 2 on the vertical axis. Okay, so we have two budget sets, this one or this, and we have this budget set or the new budget set. Okay? Under the previous budget set, we observed that consumer choose this bundle. Okay? And under new budget set, we observed that consumer choose this bundle. Okay? But under the new budget set, the two bundles were affordable. But we observed that consumer choose this one rather than this one. It means, this bundle, let me call this x prime. Okay, and then let me call this x. And we can say x prime is labeled preferred to x. Okay, so we obtain this preference ranking. All right. So, but under the previous bundle, under the previous budget set, we observed, consumer choose bundle x instead of x prime. That means x prime is not affordable. So x prime must be outside of this triangle, just like this. Okay? So if we observe this kind of pattern, this kind of consumption pattern in the data, it means it is consistent with the warp. So it satisfies the weak axiom. Okay? But in the second figure, so still we have two budget sets, this one and this one. Okay? But in either budget set, two bundles are affordable. Yeah? But with this budget set, we observe that consumer chooses this one. Okay? So let me call this x prime. And under this budget set, we observe that, so we observe the consumer choose this bundle x. Okay? So if you think about the this budget set, the consumer's choice, okay, reveals that he prefers x prime to x. Okay? But based on the second budget set, although two bundles are affordable, we observe that consumer choose this one. That reveals x is preferred to x prime. Okay? Now the preference ranking is reversed. That is a violation of this warp. Okay? So the warp can be thought of as the completeness assumption on the labeled preference. Okay? So that is kind of the assumption for minimal consistency. Okay. So now we are going to discuss three implications of this warp, and it turns out that the main takeaway of this video is, under preference-based approach, in order to establish the three properties, we needed to make several assumptions on preference relations. Okay? That is, what we can't observe. But, in this labeled preference approach, we did the warp alone and Wallace law. Okay? just with the two assumptions, we can recover these two remaining properties. So we can show that the choice function, if the choice function satisfies the verb, is going to be homogeneous of degree 0, just like the Wallachian demand function. Yeah, and then if the choice function satisfies the verb and the Wallace law, then it can be shown that Slotsky matrix is going to be negative semi-definite. Okay, so I'm going to discuss one by one. So here is the first implication of the verb. Okay, so the theorem states that if the choice function satisfies Wallace law and the verb, then the choice function is going to be homogeneous of degree 0 in the price vector and W, just like the Wallachian demand. Okay, and the way to prove this is really simple. So let me go through the proof in this lecture video. Okay, so to prove this statement, we needed two price vectors and two wealth. Two levels of wealth. So we first have P and W, and then the observed data. So the actual choice made by the consumer is given by bundle X under this budget set. And then we increase P and W alpha fold like this. So P prime indicates alpha times P, W prime indicates alpha times W. And then the actual choice made by consumer is given by this bundle X prime. And then what we want to show is that this choice function is homogeneous of degree 0. It means the bundle X prime is equal to bundle X. That is what we want to show. And the way to prove this statement is, just as usual, we're going to use the proof by contradiction. So we suppose the contrary, that X prime is different from bundle X. These two bundles are different, and we're going to derive some contradiction. So first, what we can say is, because we know Wallace law is satisfied. So let me first apply this Wallace law to X prime, because X prime is the actual choice under this configuration. And because by this Wallace law, we know that P dot X, so P prime dot X prime is equal to W prime. But by definition of P prime and W prime, it can be written as alpha P dot X prime equals alpha W. And alpha is a positive constant. So canceling out this alpha, then we obtain P dot X prime equals W by Wallace law. And that means the new bundle X prime is affordable under the previous budget set, P and W. And X is also affordable, but we saw that consumer chose the bundle X instead of X prime. So by the weak axiom, we can say P prime dot X should be larger than W prime. Once again, the two bundles are affordable under the previous budget set. We saw that consumer chose this bundle X. It means X is liberally preferred to X prime. Then why did we observe X prime under this configuration? Because under this budget set, bundle X is not affordable. But P prime is alpha P and W prime is alpha W. So we can rewrite this inequality by P dot X is larger than W. But that contradicts with Wallace law. If we Wallace law to x, then we must have p dot x should be equal to w. Okay, so that is a contradiction with this inequality. All right, so that contradiction gives us the so we started from this presumption x prime is different from x, and this contradiction implies that our presumption is wrong. Okay, x prime must be equal to x. In other words, our choice function is homogeneous of degree 0. So I think this proof is doable. But the second implication, okay, so now we are going to show that so we are going to make assumption so we are going to assume that choice function is differentiable, okay, and it satisfies the Wallace law and verb just as in the previous statement, okay? And it turns out that Slotsky matrix is negative semi-definite, okay. So you may wonder that because we are not taking the preference-based approach. If we took the preference-based approach, then we can obtain the Hicksian demand, and so we can define the Slotsky matrix. But now we work with just the choice function alone. Then how do we define the Slotsky matrix? Okay. Previously, we defined the Slotsky matrix as the derivative matrix of a Hicksian demand. But without the Hicksian demand, how do we define the Slotsky matrix? And the idea comes from Slotskycation, okay? Because by the Slotskycation, we can, so, each entry in this Slotsky matrix stands for the substitution effect. So, for example, this derivative. So the entry in this, one entry in this Slotsky matrix, H1, the derivative of H1 with respect to P2, it stands for, so it measures substitution effect on demand for good one when price of good 2 changes. And by the Slotskycation, that can be expressed as the total effect. So Wallacean demand, so derivative of Wallacean demand with respect to P2, that is a total effect. Yeah. And then we subtract away the income effect, but the general sign of the income effect is a negative in the in the Slotskycation formula, so it can be positive. So now it will be back up to be positive. Yeah. So we subtract away the income effect. That is going to be derivative of this Wallacean demand with respect to income. Okay, and we multiply by Wallacean demand for good 2. Okay, but now we work with a choice function instead of this Wallacean demand function. And these two functions, although they are different, right? But these two functions share the common property. The two functions depend on price vector P and the consumer's wealth W. Okay. So after replacing this Wallacean demand with the choice function, we obtain this one, x2. Okay, so in this way, we can formulate the Slotsky matrix in terms of the choice function. Yeah, so once again, the Slotsky matrix with this choice function is defined as the collection of these entries, S sub ij. S sub ij stands for the substitution effect on the demand for good I in response to change in the price of good j. Yeah, and by the Slotskycation, this substitution effect can be expressed as the total effect on the demand for good I minus the income effect, the corresponding income effect. Yeah. So now we are going to show that this Slotsky matrix, so consisting of these entries, is a negative semi-definite. So the proof is a little bit technical. Although the proof of the first theorem is quite simple, this one is slightly complicated. So I want to highlight that. So let me say first, before we proceed to the proof, let me say, yeah, you may skip that if you are not interested in the theory. So if you're not interested in the theory, you may skip the proof of this theory. Okay? Once again, this is a technical. All right. So yeah, I'm not going to take a supplementary lecture video. So let me go through the proof in this main lecture video. But once again, you may skip that. I will not test on the proof of this theorem in the exam. Okay. So the way to prove this statement is, so we need two different budget sets. Yeah. In order to make use of this verb. Yeah. So X0 stands for the consumer's choice under this budget constraint. Okay, so X0 is X of P0 and W0. Okay, and then we need another budget set. Okay, so we need another price vector P1 that is different from P0. Okay, but where it is adjusted as much as the consumer can afford the previous bundle. Okay, so this is a W1, but we adjust the income to the extent that consumer can afford the previous bundle. Okay, with this W1 and under new price vector P1, X0 is affordable. Yeah, so that reflects the idea of Slotsky compensation. So when we talk about the substitution effect, we discussed the two different methods of compensation: Hicksian compensation and Slotsky compensation. Okay, and Hicksian compensation gives the enough money such that consumer now can go back to the old indifference curve. Okay, so we preserve the level of utility. Okay, so under that compensation, we measure the size of substitution effect. Okay, and another compensation is the Slotsky compensation, and the second compensates the consumer as much as now with that compensation, consumer can go back to the original bundle. So this idea reflects the idea of Slotsky compensation. Okay, so we adjust the income as much as consumer can get back to the previous bundle. Okay, then under this budget set, P1 and W1, this bundle X1 and the previous bundle X0 are both affordable. Yeah, but we saw that consumer chooses X1 rather than X0. Yeah? So the verb implies that under the previous price vector, we saw that consumer chose X0 rather than X1. That means X1 is not affordable under P0 and W0. Okay, so P0 dot X1 is going to be larger than W0. Okay, but by Wallace law, W0 can be written as P0 dot X0. Okay, so the amount of expenditure for choosing this bundle under this price vector. Okay, and of course, we don't know X1 is different from X0. So if X1 is equal to X0, this inequality will be held with weak inequality. Okay? So this inequality becomes the equality. Alright, so we obtain this inequality from the verb. Okay, and then if we apply the Wallace law to X1, okay, then we obtain P1.X1. That is the choice function. That is the actual choice made by the consumer under this budget set. Okay, so by Wallace law, we must have P1.X1 is equal to W1, but W1 is given by this. Okay, so we have this equation. So now what I'm going to do, I'm going to combine these two. So I'm going to merge these two by subtracting this inequality from this equation. Okay, then on the left hand side, I'm gonna have P1 dot x0 minus this quantity P0 dot x0. Okay, and I can see common factor x0, so I can factor it out like this. So I have this on the left hand side, and on the right side, I'm gonna have P1 dot x1. Okay, and remember, I subtract this inequality from this equation. So P1 dot x1 minus P0 dot x1. Okay, and I can factor out the common factor x1 like this. So I have this. Okay, and if we compare the quantities, these two quantities, which one is larger? Because on the right side, I subtract the bigger number from the same quantity. Okay? So the left hand side must be larger than the right hand side. So we have this inequality. Okay? The inequality will be reversed like this. Okay, then remember P1 is any other price factor than P0. Okay, so we have a lot of freedom on the choice of this P1. Okay, and let me choose P1 as the P0 plus Ty. Okay, that means in the price vector P1 and P2, in case of two commodities, if this is a P0, okay, now I'm gonna slightly change this vector to P1 in the direction of vector Y. Okay, and the size of this vector is going to be T. Okay, so the new vector P1 is going to be this one. Because we have a lot of freedom on the choice of P1. Okay, so given P0, we can move this vector into any direction. So the directional vector Y is arbitrary vector. Okay, and T is also arbitrary. Okay, as long as T is larger than 0, we're going to obtain the different vector. So we're going to obtain vector P1, which is different from P0. Okay, so after choosing this P1, let me substitute this P1 into this inequality. Then P1 minus P0 is going to be simply Ty. Okay, so I'm going to have Ty dot x0 on the left and Ty dot x1 on the right. And T is a positive constant, so let me cancel out these two T's from both sides. Okay? Then inequality reduces down to this one. Okay? And remember, x1 is the actual choice made by the consumer, the chosen bundle, under price factor P1 and this W1. Okay? Now we choose P1 as this one. Okay? So I can substitute this quantity, this vector, instead of P1. Okay? And x0, remember x0 is the chosen bundle by the consumer under price factor P0 and W0. But W0 is P0 dot x0 by the Wallace law. P0 dot x0. Alright, so now I'm going to transform this inequality into the another inequality in terms of this function f. Okay, so let me define this function f as a function of t. Okay, so this function this function f of t is defined as y dot this choice function. Okay, And by definition of x1, then the right side becomes f of t. Okay, originally x1 is a function of price factor and wealth, right? But with this parameter t, I can transform this given function x into the function of t, just like this. Okay, now what is the left hand side? Because x0 is the chosen bundle by this function x under this configuration, but that configuration is equivalent to the case when t is equal to 0. Okay, so you can easily verify that this quantity amounts to f of 0. Okay, so we have this inequality. F of 0 is larger than f of t. Okay, once again, we have a lot of freedom on the choice of t. T was the size of this vector. Okay, so for every t, we have this. That means if we reformulate this inequality in terms of the function f of t, then we can see that function is globally maximized at t equal to 0. Okay, so we don't know the exact graph of this function, but at least in the neighborhood of 0, this is f of t. In the neighborhood of 0, the function must be decreasing, like this. If the function is increasing at 0, then clearly f of 0 is not a maximum point. It means at least we can say the sign of the derivative at 0 is non-positive. Non-positive. Yeah. So I think you can follow the proof up to this point. It's not that difficult. Yeah? So the only non-trivial part is the way to transform this inequality into the inequality in terms of function f. Yeah? But the basic structure of the proof is not that complicated, except the last part. So now it remains to take the derivative of this function with respect to t. Okay, but this function is vector valued and a multivariate function, meaning that in case of two commodities, x, p, and w is a vector valued. So we have a two tuple vector. It tells us what is the demand for good 1 and what is demand for good 2. Right? And this function also depends on multivariate multivariables, because price vector p is a p1 and p2. It also depends on w. So this function depends on 3 tuple vector at least. Okay? But now we are considering the derivative of this function with respect to t. So after multiplying the inner argument t-fold, so p becomes tp, w becomes tw. Okay, and then we take the derivative of this function with respect to t. Okay, and the way to calculate multivariate functions derivative is so let me start with a very simple example. Say, suppose that we have function g depends on x1 and x2. Okay, and let me rewrite this in terms of vector form. So here vector x is a x1 and x2. Okay, and then let me multiply the inner argument by t, so g of tx. Okay, now what is the derivative of this function with respect to t? Once again, this is not vector valued, but this is a multivariate function. It gives us a scalar, but depends on 2 variables. And because if we multiply t to the inner argument, then it's going to be tx1 and tx2. So the derivative of g is going to be total derivative. So g sub 1, the partial derivative of this g with respect to x1, and we multiply by x1 by the chain rule. Okay? And then we needed to consider the change in g due to change in x2, because change in t induces the change in x2. Yeah? So that will be captured by g sub 2 times x2. Yeah, so that is the basic idea of a total derivative, and it can be written as a gradient vector of g and dot product vector x. So this vector x is x1 and x2, and gradient vector g is the g sub 1 and g sub 2, the collection of the partial derivatives. Okay, and we can rewrite this. So this is the so we express the total derivative as the dot product, but we can express this total derivative with a multiplication of two matrices. Okay, so it can be written as gradient vector of g times matrix x. Okay, but for multiplication of matrices, we should be careful about the dimension. So because x is defined as x1 and x2, that is a 1 by 2 vector. Okay, and the gradient is also 1 by 2. So 1 by 2 times 1 by 2, so that multiplication is not defined. Okay, but the way to resolve this dimension issue is we take the transpose, okay, on x. Okay, then that is going to be 1 by 1. The result is going to be 1 by 1, because x transpose becomes 2 by 1. Alright, so that is the way to take the derivative of multivariate function. Now we consider vector valued and multivariate functions derivative. Yeah? In case of vector valued, if we take the derivative with respect to t, then it becomes, so now the x becomes the derivative matrix of x with respect to p, because t appears in the place of t, so in the place of t. Yeah? So if we take the derivative with respect to p, x is a vector valued, and p is two-dimensional vector as well, p1 and p2. So the derivative is going to be 2 by 2 matrix. Okay, once again, you may skip that if you're not interested in the theory. Okay, and if you're not interested in the vector calculus, okay, that is totally fine. And then by the chain rule, we needed to multiply by the vector p. Okay, but we already expressed the derivative in terms of a matrix using the derivative matrix, right? So we have to multiply by p. Okay, now we have to determine the dimension of each matrix. So the derivative matrix is L by L. So 2 by 2 in this example. Okay, and vector p is 1 by 2. 1 by 2. So we have to take the transpose. Okay, and then t also appears in place of w. Okay, but w is a scalar, unlike the price vector. Okay, so the derivative is going to be gradient of x with respect to w. Okay, and then we multiply by the derivative of this guy with respect to t by the chain rule. So we have additional w here. Alright, so that's the way to take the derivative. So now using that, let me figure out the derivative of this function with respect to t. how to calculate the derivative of this function with respect to t. So f prime, the f of t is given by the dot product between y and x. Okay, and then let me rewrite this using the multiplication of matrices, okay, instead of dot product. Okay, so vector y is a so that is 1 by L, 1 by L, 1 by L. So let me say vector y is given by L by 1, L by 1. Okay, and vector x is also given by L by 1. Okay, then okay, then in terms of the product, I have to take the transpose on y. So y transpose times x just a sec. L by 1, 1 by L. Yeah, I think it's better to say this is 1 by L and this is 1 by L2. Yeah, let me set this is 1 by L, and this matrix X is a L by 1. L by 1. Does it make sense? L by 1. Yeah, okay. Then we don't have to take the transpose. So y times matrix X is well defined. Okay, dy. Yeah, I'm not sure, but I think in my eyes, yeah, this is perfectly fine. Okay, and then let me take the derivative. Okay, then y is independent of t, so leave it alone. All right, and then t appears in two different spots, here and here. So in place of price vector p and in place of w. Okay, so the derivative with respect to p, or with respect to t, is going to be two pieces. So first, the derivative matrix of x with respect to p, okay? And then we multiply by vector y. Okay? But we assume that vector y is a 1 by L matrix. Okay? And the derivative matrix is going to be L by L. Right? So we transpose, we have to take the transpose on this y. So y becomes y transpose. Okay? And plus that considers just the price effect. Now we have to consider wealth effect, because change in t brings about the wealth effect as well. So that's going to be gradient vector of w. So gradient vector of x with respect to w. Yeah. And if we take the so by the chain rule, we are now multiplied by, so we have to multiply by y times x0. Yeah. But we take the transpose. So y times x0 transpose gives me x0 transpose times y transpose. Because in general, if we take the transpose on AB, the product of these two matrices, then we obtain B transpose times A transpose. Okay? So we have this. All right, so I can see common factor y transpose, so I can pull it out. Then the remaining terms is going to be dpx plus times x0 transpose times yt. Okay. Also, this is L by L, and this is L by 1, and X transpose is 1 by L. Am I right? So X was defined as L by 1 vector. X transpose is 1 by L. Okay. So everything makes sense. Okay. And the summation between these two is well defined as well. Okay, and then we evaluate this derivative at 0. Then X becomes at 0. Okay. So when t is equal to 0, X becomes x0. Okay. So f prime of 0 is going to be y times dp of x at x0 plus gradient of x with respect to w at x0 times x0 transpose. All right, and this is, so the expression in the bracket is going to be the Slotsky matrix. Okay, so the first term, the price of the total effect, is given by this derivative matrix, and this partial derivative with respect to income is captured by this gradient with respect to income. Okay, and then this x is given by this x transpose. Okay, so that is going to be, so this guy is going to be L by L matrix, and its ijth entry is going to be substitution effect on demand for good I with respect to change in price of good J. Okay, so because we know that if the sign of the derivative at 0 is non-positive, okay, so this should be non-positive for every directional vector y. That means the matrix in this bracket is a negative semi-definite. Okay, so this was the Slotsky matrix P0 and W0, but P0 and W0 chosen arbitrarily. So in general, Slotsky matrix is negative semi-definite. Because the definition of a negative semi-definiteness is every quadratic form Y transpose is non-positive for everyone. Cool. So once again, this is slightly technical. So, but if you are interested in doing theory, okay, and you wanna, so if you wanna exactly understand the proof of this statement, but you don't understand my explanation, feel free to contact me. Okay? So for those who are not interested in theory, it is enough to know that warp implies the negative semi-indefinite Slotsky matrix, just like the Hicksian demand. Okay. A little subtle part is how do you formulate the Slotsky matrix with this choice function without the Hicksian demand. Okay, and the idea comes from the Slotsky equation. I think that is enough. And just one more implication from the warp is the so the law of compensated demand. It should be typo. This is a law of compensated demand. Yeah. All right. So this law tells us. Okay. So let me read the statement first. So if this choice function x satisfies Wallace's law and the warp, okay, so we have the same condition. Then we have the dot product between these two. So p prime minus p, that reflects the price change. Okay? And x of p prime w prime minus x of p and w, that reflects the so that measures the change in demand. Okay, the dot product between change in price and change in demand is non-positive. Okay, but one important thing is here W prime, the consumer's wealth is adjusted. Okay, adjusted such that now consumer can afford the previous bundle under new price factor. Okay, so just like the Slotsky compensation. Yeah, so here we have the original bundle. Okay, and we observed the consumer choose this bundle. Okay, and under new price factor, we adjust the income as much as consumer can go back to this original bundle. Yeah, so the new budget line will still pass through the original bundle like this. Okay, so that is kind of compensated demand. Okay, so we observe the consumer's demand after compensation, after adjustment of the income, as much as he could go back to the previous bundle. Okay, and then if we think about the meaning of this inequality, okay, so that is related to the interpretation of the dot product. So the dot product between two vectors is formally defined as so it can be defined as this way. So there's the magnitude, so the norm of a vector x, this is too much, and the norm of a vector y times cosine of theta. And here theta stands for the the angle between these two vectors. Okay, so the sign of the vector, the sign of the dot product tells us the so it gives us information about the angle between these two vectors. So if the it's enough to know this one. Okay, if the dot product between these two vectors is positive, then the angle, so the angle between two vectors, say this is a vector x and this is vector y. Okay, the angle between these two vectors, theta, that is acute. Okay, so that is smaller than 90 degrees. And if the dot product is equal to 0, then the theta is going to be that is equal to 90 degrees. Okay, the meaning that the two vectors are perpendicular to each other. Okay, like this. And if the dot product is a negative, then theta is obtuse. Okay, so it is larger than 90 degrees. Okay, so what happens the angle between these two vectors is larger than 90 degrees? It means if we have a vector x here, okay, now we have obtuse angle, so like this one or like this one. Okay, so vector y should indicate this direction or this direction. Okay, inside this range, inside this range. It means the movement of these two vectors are different. Okay, so if x indicates this direction, but y indicates the other direction. Okay, so with that interpretation in hand, if we go back to the this dot product, so this inequality tells us change in price and a change in demand and after compensation. Okay, so the change in compensated demand indicate a different direction. Okay, so that is kind of the general version of the law of demand. So the standard law of demand in principle of economics tells us demand curve is decreasing. So if we have x1 and p1, and demand curve for good one is decreasing over price. Yeah, so that okay, so the law of demand can be thought of as the so it can be interpreted as the negative association between the the price movement and the change in demand. Okay, and its general version can be written as this dot product. Okay, so if we have two goods, P1 and P2, so price factor is given by P1 and P2, and the demand X is X1 and X2, then this, and so if we consider the change in P1 only, okay, then this is going to be change in price of change in P1 only, and multiplied by change in demand for a good one. That is a negative value. Okay, so that means the change in price of a good one and change in demand for a good one will indicate the opposite direction. Okay, so they will move in the opposite direction. Okay, so that is kind of the law of demand. All right. So so this is kind of a compensated demand. So it is very similar to the Hicksian demand. So if we adjust the income by way of a Hicksian compensation, so we compensate the consumer's income as much as the consumer could go back to the previous indifference curve, then this change in demand can be captured by the difference between the Hicksian demand. That is going to be so this guy is going to be H of P prime and U minus H of P comma U. Okay, if we consider Hicksian compensation. Right, then this law of demand tells us price change in P and the change in Hicksian demand indicate the opposite direction. So let me first prove this statement. It has nothing to do with the verb because in the liability preference approach we don't have discussion about the Hicksian demand. Okay, but even by taking the preference based approach, we can prove the law of compensated demand. Okay? Because that is important. So in preference based approach, I'm sorry, this lecture video is not that organized because I went through this complicated proof. After that, I think it is a little bit disorganized, but yeah, let me highlight this fact. In preference based approach, we can show that the law of compensated demand. So P prime minus P dot H of P prime U minus H of P comma U is always non-positive. Okay, and the way to say this is really simple. That is immediate from the definition of Hicksian demand. Okay, so let me distribute the difference between these two to P prime. Okay, now I'm gonna obtain P prime dot H of P prime U minus H of P comma U. Okay, and distributing the same difference to P, I'm gonna obtain minus P dot H of P prime U minus H of P comma U. Okay, now think about the sign of each quantity. Yeah, so in the first multiplication, in this dot product, we have P prime dot H of P prime. Okay, what is that? That is a minimal expenditure. Okay, so P prime dot H of P prime, that is a minimal expenditure function at P prime and U. Okay, so it tells us what is the way of minimizing expenditure under price factor P prime in order to obtain the target utility U. Okay, so if we compare that with P prime dot H, there is another demand schedule. Okay, but that is different from this H of P prime. So P prime dot H will be larger than this expenditure function by definition of this Hicksian demand. Okay, so we can say this is a negative. Now think about the second quantity, the sign of the second quantity. We have P dot HP prime and then P dot HOP. Okay? P dot HOP is the minimum expenditure under price factor P. Okay? So if we choose alternative bundle, our expenditure is going to be larger. Okay? So this one is clearly positive. Okay? So we take away some positive number from negative number, so the total quantity should be negative. Okay, so that's the way to establish the law of compensated demand in the preference-based approach. Okay, and in line with this, we can establish the law of demand, compensated demand, in the labeled preference-based approach. Okay? Now the Hicksian demand is replaced with this choice function with adjusted income, okay? By way of Slotsky compensation. Okay? And under the Wallace law and the verb, we can show that compensated demand, the law of compensated demand is actually satisfied. Actually, we can show that these two are equivalent, but that is beyond our scope. So let me skip that. But if you are interested in the equivalence, the equivalent relationship between the verb and compensated demand, you can refer to the textbook. Okay, so let me just prove that verb implies the law of compensated demand. Okay, so for the proof, let me call this x prime. This choice is x prime, and this choice x. Okay, so we want to show that p prime minus p dot x prime minus x is less than or equal to 0. Okay, and proof is really simple because p dot x, so by Wallace law, so if we apply the Wallace law to x prime, we know that p prime dot x prime is equal to income w prime, but w prime is adjusted, so income was adjusted to the p prime dot x. Okay, so we must have p prime dot x prime minus x be equal to 0. Okay, and then by the verb, okay, so this implies that under price factor p prime, the two bundles are affordable. Okay, but we observe that consumer choose this bundle, x prime, rather than x. That means by the weak axiom, so that implies bundle x prime is labeled preferred to bundle x. Okay, so by the weak axiom, we must have under price vector p, okay, x prime is not affordable. And by applying the Wallace law again to x, bundle x, then we have this equivalence. So p dot x prime should be larger than p dot x. So we have this. Okay, so if we subtract this second inequality from the first, okay, because the first quantity is equal to 0 and the second quantity is some positive number, so we have a negative number. But the difference between these two is going to be this expression or this one. Okay, so we prove that we prove the law of compensated demand. Okay, so from this figure, this is a budget set under price vector p. And this is a new budget set under price factor p prime. Okay? So x prime minus x dot p prime is equal to 0. That means x prime must be on this budget set, or on this budget line by Wallace law, because the actual choice made by the consumer when price factor is p prime should be on this budget line. Okay, but the verb implies that x cannot be right here, x prime, because if this is the case, two bundles are affordable under two different budget sets. Okay, but in one budget set, this consumer chooses this bundle, and under the other budget set, he chooses the other bundle. So that is inconsistent. So which means, under the verb, okay, so if the choice function satisfies the verb, x prime must be on this line segment. So x prime must be somewhere on this line segment. Okay, so the price factor p, that is the perpendicular vector to this budget line, the original budget line. Okay, and then x prime minus x, that's going to be, this is x prime, and this is x. Okay, so we have this vector. So the angle between these two must be acute. Okay, less than 90 degrees. Just as predicted by this inequality. Okay, so dot product must be positive. That means the angle between these two vectors, p and x prime minus x, should be lower than 90 degrees. Okay. All right, so that is the third implication of verb. Okay. This video is going to be pretty long. So to summarize our discussion, we just have shown that if the choice function satisfies the Wallace law and the verb, we can show that choice function is homogeneous of degree 0, and Slotsky matrix is a negative semi-definite. So the choice function satisfies these two properties. Okay, and on the other hand, Wallacean demand derived from the preference-based approach is homogeneous of degree 0, and it also satisfies the Wallace law. If we make assumption on the preference relation, and finally, the Slotsky matrix is symmetric and negative semi-definite. Okay, this symmetric property comes from the Young's theorem. So by the Young's theorem, the order of differentiation does not matter. Yeah. So the two entries so the two off-diagonal entries in the Slotsky matrix must be identical. Okay, but with the verb alone, we could show that this property, and we could recover the negative semi-definiteness. Okay, and Wallace law is satisfied in many cases. So if we assume just only goods are traded, then monotonous condition is easily satisfied. Okay, so in such a case, Wallace law is indeed satisfied. So that does not matter. But symmetry of the Slotsky equation is a not trivial thing. Okay, but here, because I skipped this topic because this is beyond our class, but if you refer to Musgrave-Winston-Green chapter 3.h, so integrability theorem was introduced. So integrability theorem is introduced in that chapter, and that theorem tells us if the choice function possesses the three properties above, it is homogeneous of degree 0, and satisfies Waller's law, and the associated Slotsky matrix is a symmetric and negative semi-definite. Then the preference ranking we can deduce from the observed data is rationalizable. Okay, once again, in the preference-based approach, we are trying to deduce the preference ranking from the observed data. Okay, then the verb just imposes on the completeness. Okay, and the other important condition for rationality is a transitivity. Yeah, so with the verb alone, we can't say the deduced ranking is rational. Okay, so deduced preference ranking is rational. Okay, it is complete but not transitive. Okay, so verb does not imply the transitivity of the deduced ranking. Okay, but if we strengthen the condition to strong version of labeled preference, the so-called strong axiom of labeled preference, SARP, then symmetric matrix, or the Slotsky matrix is going to be symmetric. Okay, and Waller's law is very easily satisfied, as I told you. Okay, the three conditions are satisfied for the choice function. So by the integrability theorem, the deduced preference ranking can be rationalized. That means there exists a utility function that rationalizes the observed data. Yeah? So I'm not going to go through this strong axiom, but it can be thought of as the recursive version of the weak axiom. Okay, so we apply the weak axiom to some sequence of bundles, sequence of observed bundles. Okay? So if you are interested in that strong version, you may refer to Musgrave-Winston-Green chapter 3.j. It appears in 3.j. Okay? But yeah, the main takeaway about the verb is just with a very mild condition on the choice function, we can recover two major properties of Wallachian demand. Okay? So we can recover the property of homogeneity of degree 0 and negative semi-definiteness of the Slotsky case. Furthermore, we can show that the law of compensated demand. Yeah? Right? But because we can show the symmetry of the Slotsky matrix. So we can say the deduced ranking is transitive. Okay, so we can say the deduced preference ranking is rational. Okay? But if we strengthen the verb to the strong version, okay, SARP, and we can show the Slotsky matrix is even symmetric. Okay? So by the integrability theorem, then we can make sure the existence of a utility function that rationalizes the observed data. Alright, so this is a long discussion about the labeled preference. So hope you enjoyed this video. And once again, if you have any questions about the course material, don't hesitate to ask me at the live lecture. Alright, so hope you have a nice day.